Quantum Mechanics, Localization by Resonant Reduction, and Logic, recently published. There are many views of quantum mechanics. Feynman said it's crazy, it doesn't explain anything, it just gives you numbers. Einstein was more critical. The wave function does not provide a complete description of the physical reality. I will show you a description which is dual harmonic and takes place in time. Matter is uncertain. All quanta are harmonic. You count the nodes, 1, 2, 3, 4. The quantum is a property, not an entity. Entities should not be multiplied without necessity. I'm going to compare evolution of states in math with hidden variables in physics. Math is in red, physics is in green. The third axiom is uncontentious. The unitary evolution of isolated systems is deterministic and continuous. That is and has always been typical of physics. What about completeness? The rays of Hilbert space correspond one-to-one with the physical states of a system. Well, what does that mean? If what they mean is that abelian matrices solve in closed groups, there may be something in it, but that's not what Einstein meant, as we shall see in the next axiom. Feynman claimed that he could not predict changes in the future theory like this one. And the completeness seems to be at odds with Gödel's theorem about axiomatic systems. Let's move on to measurement. If the emission operator A with spectral detectors P, the probability of outcome is this bracket. These probabilities are objective and indeterminate. Again, what does objective mean? It seems to be ambiguous. For Einstein, it meant that conservation laws of physics are not void and that reference frames do not vary randomly. But on the other hand, all measurement is indeterminate. That's why we add error bars to our measurements. Some error bars are due to variables that are known but not measured, or not known and not measured, or statistical, known and measured. We'll come to examples of these in a short while. And we can now skip to the fourth axiom, which is the most contentious of all. Evolution of systems undergoing measurement are discontinuous and instantaneous. Well, how can that be? What happened to the uncertainty principle in time? We find that the changes must be continuous in a time which is given by a formula which we should derive and influenced by hidden variables. Dispersion dynamics, mass, uncertainty, internal motion. 3 parts. Wave-particle duality. We begin by uniting Newton's corpuscles, Huygens wavelets, Fraunhofer's and Fresnel's Young slits, Lloyd's mirror, and Maxwell's electromagnetism gave a very good understanding of electromagnetic phenomena at the end of the 19th century. Then came the quantum, discovered at the end of the century, and developed with Planck's law, de Broglie's hypothesis, Einstein's special relativity, energy squared as momentum squared plus mass squared, and express it in simplified units. And it gives some consequences, but the simple expression that we get from this application of quantum theory to wave-particle duality is that m squared is omega squared minus k squared. Mass squared is angular frequency squared minus the wave vector squared. And this separates into 2 parts. A conservative part, which describes mass, charge, spin, energy, momentum, and a response part, which describes interference, superposition, creation, annihilation, entanglement, and resonance. The solution to this equation can be given by a wave equation, which separates into a conservative part and a response part. The conservative part is an envelope function. The response part is an infinite wave with unit amplitude for all x and t. We're going to operate on these equations. And the 2 operations that we need for this paper are the Fourier transform and differentiation. Notice first of all that mean omega and mean k are mean values of varying functions. And the first thing we're going to do is notice that from the figure we saw in the previous slide, the uncertainty in position is 2 sigma. That's the width of the Gaussian envelope. If we Fourier transform that, we get an equation of this type, and if we normalize the exponent, we find that d omega is 4 over sigma. When we multiply these two, sigma cancels, and we find that the expected uncertainty, d omega by dt, is 8, and in position is the same, equal to 8. This is an order of magnitude greater than Heisenberg's limit, as it should be. The second operation we perform is differentiation. If we differentiate that equation, we get a very simple result. The product of the phase velocity and the group velocity is equal to c squared. Omega over k is equal to nu times lambda. It's the speed of the velocity of the carrier wave, and d omega by dk is the speed of a beat of 2 tuning forks off tune. It's the group velocity. We know what the group velocity is because it's the velocity we use in special relativity. It's less than c. And the phase velocity is the inverse of the group velocity. It's greater than c, with speed approaching infinity as the wave vector approaches 0, or as the wavelength approaches infinity. So that's the wave packet that we're going to use again in a moment. But first, what do we mean by quantum? What are some examples of quantum? Schrödinger's harmonic eigenstates in hydrogen, line spectra and atomic emission and absorption spectra, the wave packet we've just described, momentum quanta in crystal diffraction, and dual harmonics in hierarchic crystals. Momentum quanta are simple quanta because they can be easily visualized in terms of harmonies. Here's a comparison of diffraction patterns in natural and irrational solids. The second phase of melt-spun aluminium-6 manganese is crystalline. The probe is harmonic, the crystal is harmonic or periodic, and the diffraction pattern is periodic, follows Bragg's law. The order n is given here, 0, 1, 2, 3, 4, 5, 6. In this instance, odd orders are suppressed by structure factors because half the atoms scatter in antiphase. Well, that's the crystal. N is integral, periodic and harmonic. The harmonies are extremely well understood in crystallography. Quasicrystals are completely different. Analysis is commonly misled by questions of aperiodicity and fivefold symmetries. In fact, the greatest difference between these two is the order. N equals 0, 1, tau, tau squared, tau cubed. Tau is irrational. It's aperiodic. And the structure is hierarchic and not space-filling. These orders and measurements, measure variables, are different in the two formulae. And we have shown that the ratio between theta and theta primed for corresponding reflections is equal to a metric CS, which is the same for all orders. Look at it in a little more detail. You can show by mathematical induction that the irrational number tau to the m is equal to this Fibonacci number. 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, 3 plus 5 tau. Notice it separates into a natural part and an irrational part. And you can approximately naturalize this by substituting for tau the rational fraction 3/2 to find the natural part, which is quite Bragg-like. But if you subtract this from the irrational number, you get an irrational residue, which you use inside a metric function which has the extraordinary property that it is the exact inverse of the coherence factor that we discover numerically for all orders. And I'll illustrate this. Look at the blue wave. The blue wave is a block wave obtained in the two-beam condition from a crystal. It's commensurate with the unit cell, and with all unit cells periodically repeating. That's for the crystal. But it's incommensurate with the geometric quasi-lattice. However, if you stretch the blue wave by the metric function that we just saw, you find a quasi-block wave, which is commensurate with the logarithmic quasi-lattice, both long-term and short-term around each intercept. It's dual harmonic. The dual harmony compares with the 12-point scale in Western music. Perfectly understood, harmonies and Bragg diffraction confirm that all quanta are harmonic, and we're going to go on with that assumption. But refer back to Young's double slit at the beginning of the 19th century. Consider a coherent wave incident on two slits. The transmitted beams form two waves which superpose and form a wave amplitude, which a wave function which is sinusoidal and when squared gives the interference pattern. You could see this interference pattern if you were to look at it, because this is what would appear on your retina. I wouldn't advise you to do that. If you reduce the intensity of this beam, eventually you will get to a state where these weak beam scintillations are digitized. They appear one at a time, and it raises two problems. Well, if the detection is point-like, the mathematicians suppose the particle must be point-like. And then they ask, how come that this pattern, after a long counting time, approximates to this wave function? Well, they say it doesn't exist until you measure it. That raises conundrums for the physical understanding of this event. And the problem is twofold. If the wave is or the photon or electron is a particle, suppose it's passing through state B. How does the electron know whether to form this pattern or that pattern? It has to know whether A is open or closed. That requires spooky action at a distance. And then, having interfered, how does it know which of these atoms to alight on? Well, I'm going to propose a solution to this, which is independent of the mathematical view. We know that the particle, the envelope function, is uncertain, and the uncertainty exists from the time the beam passes through the slits to the time they are detected. During this time, these waves have a chance to resonate with a molecule on the scintillation screen. Presumably, the molecule is chosen by coherence between oscillations in the molecule and in the incident wave. And this causes the molecule to resonate. The wave resonates with the molecule and narrows down and deposits its energy on the molecule, while the molecule is at the same time emitting an antiphoton, which annihilates the incident photon. Well, that's what we suppose happens, and it all happens in time, not instantaneously. So we have a model that resolves the problems found in quantization. Let the point of a point particle be the center of the wave and rid these anomalies of instantaneous collapse, indeterminate and spooky transmission. And this leads us to the logic of measurement. Wave-particle duality is co-expressed by probability amplitudes. Quanta of energy or momenta are consequences of harmonic geometries. The discovery of quanta implied two anomalies: spooky action and unpredicted behaviors. A hidden variable can be expressed by a probability wave function. In physics, every event has a rational explanation. In mathematics, any event can be given by multiple explanations. In the logic of empirical physics, two or more explanations that make the same prediction are equally true. The localization of quanta is a product of hidden variables in time at emission, propagation, or detection. The reduction of the wavepacket may be continuous by resonant response, etc. Mathematical state evolutions that are normally discontinuous and instantaneous in math are timely in physics. Antisema, the physical model for reduction, shouldn't ignore the interference pattern when it is reduced in time. And we give a definition of mass. Omega squared minus k squared.